Today, we'll look at some specific techniques to calculate the entropy for solids, liquids, and gases. Last video, we saw the mathematical definition of the change in entropy. Delta S is equal to the integral of delta Q over T for the reversible process. This will serve as a starting point for the analysis of solids, liquids, and ideal gases. If we have a reversible process in a closed system, then the overall change in energy is just the heat in minus the work out, or du equals delta Q reversible minus delta del B reversible out, the first law of thermodynamics. Then we know for a reversible process, delta Q is equal to T ds, and the reversible work is P dV. So this becomes T ds equals du plus P dV. This is called the first Gibbs equation. The second Gibbs equation is very similar to this, but uses enthalpy instead of internal energy. In this case, TdS equals dH minus VdP. It is also important to remember that each of these is a state variable, and so does not depend on the process, only on the state of the system. These can also be written in specific form per unit mass, and also sometimes solve for the specific entropy, little s. So ds equals du over t plus pdv over t, or dH over t minus vdP over t. At this point, if the functional relationships are known, these equations can be directly integrated. Otherwise, tabular data is another option for pure substances. Now, getting into dealing with these equations for the various phases, solids, liquids, and gases. Starting with the solids and liquids, these can generally be approximated as incompressible, and so dV equals 0. Also, the specific heats need no distinction, so Cp equals Cv equals just C. And the change in internal energy per unit mass is then du equals C times dt. So the previous equation for the specific entropy reduces to ds equals du over t equals C dt over t, which can then be integrated to get the change in entropy to be delta S equals S2 minus S1 equals the integral from state 1 to state 2 of C dt over t. Remember that C is officially a function of t, so this may not always be easy to integrate. However, for many processes, C can be treated as a constant, its average value, so that S2 minus S1 equals C average times the natural log of T2 over T1. This easier formula is usually a good approximation, but may not be for certain liquids or for large temperature differences. If we have an isentropic process, then S2 and S1 must be the same, so the change in entropy is 0. This means that the right-hand side must also be 0. The only way this can happen is if the two temperatures are the same, or T2 equals T1. Therefore, any isentropic process must also be an isothermal process if the substance is incompressible, which can be approximated as true for most solids and liquids. Now on to gases, and specifically ideal gases. For ideal gases, we know that the change in internal energy is given by du equals Cv times dt. And due to the ideal gas law, we know P equals RT over nu. So the entropy equation on slide 4 becomes ds equals Cv dt over t plus R d nu over nu. Just like the last case, Cv is officially a function of temperature. However, R is always a constant. So integrating the change in specific entropy is given by S2 minus S1 equals the integral from 1 to 2 of Cv dt over t plus R times the natural log of nu2 over nu1. We could have also used the enthalpy version rather than the energy version, which gives S2 minus S1 equals the integral from 1 to 2 of Cp dt over t minus R times the natural log of P2 over P1. If we have at least approximately constant specific heats, then this first integral term can also be integrated to get C average times the natural log of T2 over T1, as shown here. Technically, this equation is for the previous slide, but can also be done for this one up here. When this approximation is not appropriate, the actual functional relationship of the specific heat as a function of temperature should be used. This is not a trivial process. Because it is so useful and important, someone has actually already done it for us. This is in table A17 of the textbook. I believe this is for air. The results of this are written in terms of a variable called S0. These are the actual values of the integral of Cp as a function of t over t times dt from 0 to some temperature. These values can replace the temperature integral on the previous slides, so that, for instance, the change in entropy, S2 minus S1, is equal to S20 minus S10 minus R times the natural log of P2 over P1. If we have an isentropic process involving an ideal gas, then again, the left side of this equation is 0, and we get the relationship natural log of T2 over T1 is equal to negative R over CV times natural log of nu2 over nu1, or remembering for ideal gases that R equals Cp minus Cv and K equals Cp over Cv, and doing some rearranging. T2 over T1 equals nu1 over nu2 to the power of K minus 1. It is also equal to P2 over P1 to the power of K minus 1 all over K. And pressure and specific volume are related through P2 over P1 equals nu1 over nu2 to the power of K. These can also be expressed as T times nu to the K minus 1 equals a constant, T times P to the 1 minus K over K equals a constant, and P times nu to the K equals a constant. Note that this began with the assumption of constant specific heats, and so that still applies. If the constant specific heat approximation is not applicable, we can go back to the S0 variables to get S20 minus S10 equals R times the natural log of P2 over P1. In these cases where tabular values are used, the pressure and specific volume are given in dimensionless quantities called the relative pressure PR and relative specific volume nu-R. In these cases, the ratios for the relative variables is equal to those for the normal variables. In other words, P2 over P1 equals PR2 over PR1, and nu2 over nu1 is equal to nu-R2 over nu-R1. So those are easier ways to deal with entropy for solids, liquids, and ideal gases. As usual, here is your pre-lecture example for this video, and any questions you have will be answered at the beginning of class.